All right, folks, and welcome back to our second walkthrough example of this crucial hypothesis testing procedure that we've been learning here in this module. So we're going to try something a little different with the whiteboard this time. Last time we emphasized the sequence of steps back there. This time we're going to emphasize this element that's at the heart of the hypothesis test, the comparison distribution. So the comparison distribution is basically a distribution of outcomes that we would expect if the null was true. We define the characteristics of that comparison distribution in step 2. We find critical values to figure out where that region of rejection begins in step 3. And then we place our sample score on there in step 4. So steps 2 through 4 basically revolve around this comparison distribution. It's really good to understand exactly what's happening there. And of course, what happens in 2 through 4 determines the decision you make at the end, which is the most important thing. So again, I've written a couple of pieces of information down. First, the comparison distribution generally comes from population 2. Population 2 is usually our basis of comparison. Its mean, the center there, is going to be the mean of population 2. I've also filled in a few pieces of information that we're going to need to get along the way. We're going to need to know what our alpha level looks like. So that's going to determine the size of that region of rejection. We're going to need those 3 pieces of information that we provide in step 2. The mean, the standard deviation or standard error, and the shape. So without further ado, let's jump into it. Here's our premise. So let's say that a psychologist is interested in assessing the test-taking ability of kids of low socioeconomic status, or SES. So what she decides to do is gather a sample of 16 children from low SES neighborhoods. She gives them a standardized measure of test taking. Yes, there are tests for how well you take tests. And she finds that her sample has a mean score of 40. That's their average score on that measure. So she needs a basis of comparison. She needs to figure out what average is. That's who she's comparing them to. So the average score for the general population for kids overall in this measure is 50, with a standard deviation of 10. The scores on this measure are normally distributed. You should already be able to pause at this point and pick out some key pieces of information that you have here. You already know most of what you need to know in step 2 about the comparison distribution. You already know the mean of the sample. You already know the number of people in that sample. That's going to matter a little later on too. And it looks like you probably have a pretty good idea what the hypothesis is, the alternative hypothesis, which means you can figure out the null pretty quickly. So always be prepared to pause midway through these descriptions and take stock of what you know. What can you identify? What key pieces of information are there? When are you going to need to use them? A little more information. We are going to decide if kids from lower SES neighborhoods have lower test-taking skills than average children. We're also going to use an alpha level of 0.05, and notice that's already one of our useful pieces of information. It can be a good idea to just write out the information you're going to need to know even before you start the question, and just fill it in as you go. If you can just keep track of what am I going to need to pick out of here, it can be really, really helpful to just lay that out in advance and then just pluck those pieces of information out as you get them. So here we already know several key pieces of information. We could even fill in that board already. We're not going to just yet, but there's a lot that we already know and not that much left to figure out. It's just a matter of remembering the structure and how it works. So step 1, we have to make up 2 hypotheses, an alternative and a null hypothesis about our populations. But first we need to figure out what those populations are. Population 1 is generally the one represented by our sample. Here, that would be kids from a lower SES neighborhood. Now note that we are talking about the population. We're talking about every single kid from a lower SES neighborhood, not just the 16 in the sample. Pretty common mistake to just wind up describing things in terms of the sample. That's not how it works. That sample is how we're representing that much, much larger group. Population 2 is our basis of comparison. We could say average children. We could say the general population. We could say kids overall. Don't worry too much about the precise phrasing here. Just get the idea right that we're comparing them to overall a very large group of children. So we're looking at typical children or children as a population. So our null hypothesis is essentially the opposite of our alternative hypothesis. Sometimes it can help people to do the alternative hypothesis first, but generally we state the null first. So what was the original prediction or the original thing we were testing? Do these kids in low SES neighborhoods have lower test-taking scores than average children? So the opposite of that is the prediction. that population 1 doesn't have lower test-taking skills than population 2. Notice there are two possibilities folded into this. The two populations could be exactly the same on that measure, or population 1, the low SES kids, could actually do better on the measure than average kids. The null hypothesis is what the researcher is actually looking at and actually probably expects, which is that population 1, the low SES kids, will have lower test-taking skills than population 2. mu1 is less than mu2. Again, with phrasing here, you don't have to say it exactly the way I'm writing it. You can plug in the low SES kids and the kids overall. You can just use the symbols. You can plug in specific numbers, like we know what mu2 is at this point. You just have to convey the basic information about what relationships each one is covering. So that's step 1. Step 2 is where we get into our comparison distribution. Again, we had almost as much information as we needed about that. We have to go through one step to fully fill out what we need, but we know the mean of population 2, that's kids overall. We know that that mean is 50. We also know that it follows a normal curve, and that's our shape information. So that, again, is 2 of the 3 pieces, but we need a measure of variability. Now, we were given a standard deviation. It was 10. Do we stop there? No, because we have a sample size larger than 1. We have to adjust it to a standard error. Remember all that talk about the sampling distribution and the central limit theorem to all just boil down to turn the standard deviation to a standard error? That's what we're doing at this step. We're converting it to account for the lower variability in those sampling distributions. So we know the standard deviation is 10 of the population. We know that our n, our number of people, is 16. We take the square root of 16, and by the magic of made-up numbers, it turns into a round number, which is 4. We divide, we find that the standard error is 2.5. Notice that that's substantially smaller than the original standard deviation, so our sample mean is not going to need to be as far away from the population mean from mu2 as an individual score would. We now have less variability there, so it's easier to get a big z-score. All right. So that's 2.5. So then we want to find the threshold or critical value. The first thing to consider is our alpha level, which is 0.05. That means the most extreme 5% of the distribution is going to let us reject the null. The other 95%, we will fail to reject or retain it. The other thing to think about, is this a one or a two-tailed test? Well, we had a directional hypothesis earlier for our alternative hypothesis. We were only predicting effects in one direction, so it's a one-tailed test. And specifically, since we're predicting that mu1 is less than mu2, we're looking at scores that are below mu2. So let's call that line what separates our region of rejection. Again, to recap, any score that we get, if our sample mean is over that line, if it's farther into the tail, we are going to reject the null. And if it's anywhere in that other 95% of the distribution, we're going to retain the null or fail to reject it. Okay, so how do we figure out if a score is in that region of rejection or not? We need that threshold or critical value. So our alpha level is 0.05. It's all in that region of rejection in the one tail, so it's just the bottom 5%. Were it two-tailed, it'd be the bottom 2.5 and the top 2.5%. That's how we'd split that 5% up. But anyway, if we use the normal curve table, or we use software like statisticians do, we find that in that tail, to happen less than 5% of the time if the null was true, you would need a z-score of at least negative 1.65. You'd have to be at least 1.65 standard errors below average to be in that bottom 5%. So that's the line that's going to separate our region of rejection from everything else, from the area where we retain things. Again, anything over that line has a lower probability than alpha. We've decided that's unlikely enough that we're going to reject the null. We're going to consider it falsified. Anything that is short of that line is happening more than 5% of the time if the null is true. So that means we would retain it or fail to reject it. So we have to calculate our z-score. Remember that the z-score formula changes a little bit with sample means. It's now the sample mean minus the population mean on top and the standard error on the bottom. Sometimes people remember to calculate the standard error in step 2, then they forget to plug it in here, in step 4. It's really, really important to use it here. That's your new denominator. That's how you standardize that z-score. So that sample had a mean of 40. That's our sample mean. We have to place it on the comparison distribution by using mu2, which is 50, and the standard error, which is 2.5. So 40 minus 50, that's the mean minus the population mean. That gives us our deviation score. The sample mean is 10 points below the population mean on that test taking abilities exam. We give it context by dividing it by the standard error, which is 2.5, and we find -4. Don't lose track of those negative numbers. So our z-score was -4. Now what we can do, and we can do this visually if we want, or you can just do it in your head, we place this on this distribution. So here's the line for -1.65. What side of this line is -4 on? Is it to the left and farther away from the mean, or is it to the right and closer to the mean? It's on the left, and it's way far out here too, somewhere like here. So our actual z-score is -4. That is not only beyond the threshold, it's like a mile past the threshold. It is far less likely than 5% that we'd see a result like that if the null was true. So what's our decision? We're going to reject the null hypothesis. We found compelling enough evidence to throw that null hypothesis out. We now believe the alternative hypothesis, which in this case is kids from low SES backgrounds as a population, not just those 16, appear to have lower test-taking abilities than average children. We have what we'd call a statistically significant difference. Now here's the kicker on this, and here's how I kind of tease you for the next video, which is that even though we managed to reject the null, there is still a probability that we made the wrong decision. In the first example, when we failed to reject the null, there's still a probability we made a wrong decision. How we label those decision errors and how we account for them is going to be the topic of our next video. So I'll see you there.